longer as we go along, but we'll see. All right, for those who don't know who I am, I'm Dr. Sirola from the Department of Physics and Astronomy, and I am a Department of Astronomy as such. We're going to take a look at what's coming up in, well, a week. It's, we'll talk about specific times to go observe the eclipse here in Hattiesburg and what to do. It's next Monday. Now, here's an interesting thing to say just as an opener. And this gives you kind of an idea of what the level of the science is. I was an instructor at a small community college in South Carolina back about 20 years ago. And I knew the date and the time for that eclipse back then. And so I was able to tell my students, hey, if you're still here in 20 years or thereabouts, you'll get to see this awesome eclipse. Well, now it's 20 plus years later, and here comes an eclipse. So this is a nickname they're giving it. That's a usual they, who nobody knows who they are. It's just a general way. I didn't come up with it myself, but I have no compunctions against stealing a good title, so I'm going to go with that. All right, so what is going on for this? A couple of intro things then. First off, this is a picture showing the continental United States primarily and the path of the eclipse. What you're specifically looking at here, the blue line right here is the very center of the eclipse where you're going to see the maximum amount of eclipse possible. The shaded areas here in this little arc that's going across is where you get at least some part of totality. We'll talk more about what we mean by totality in a moment, but that's where you're going to see the total solar eclipse. Now, are you going to see any eclipse if you're somewhere else? The answer is yes, you're going to see an eclipse. In Hattiesburg, we're going to get a little over 80% maximum coverage. So you will have an eclipse happening in Hattiesburg, so if you're not able to travel to any place along this strip, then you will be able to see at least some kind of eclipse here. I personally am, since I used to live in South Carolina, as I just mentioned, I have in-laws there. I'm not going to be here. I am traveling to where it's going to be a total solar eclipse, so I'm sorry, I'm gone. It's, the eclipse is coming, and I'm out of here. You know, so, in any case, this is not the only solar eclipse that's going to happen in the next couple of years. We'll wrap up telling you when the next ones are, as a matter of fact. All right, so before we do about anything else, this is one thing that I think is worth emphasizing to everybody, and that's how to look at it safely. And so there's a variety of different ways to do that. Now, if you happen to be an astronomer by trade, have one of these kind of interesting things, astronomers use a variety of solar filters that they can attach to the fronts of their telescopes. I've got an example here, and if you look at it, at first glance, it just looks like a mirror. It just looks like it's reflecting light. What's actually doing, this is what we refer to as a neutral density filter in astronomy, meaning that all it does, it doesn't care what wavelength the light is, what color it is, it just simply eliminates light. Now, how much light? As the joke likes to go, 99.99% of the light. It really does decrease the total amount of light that comes through. And even with that, if you use this with the telescope, it's still kind of bright to look at through the telescope with the filter on. What you end up getting with the neutral density filter, you get kind of a yellowish, orangish disk, which is basically the color of the sun normally on its own anyway. And realizing that the atmosphere of the Earth actually changes its color a little bit too. But this is an actual solar filter. So if you wanted to, and I'm not, unfortunately not going to do this, but if you were to take something like this and go look in the sky at the sun right now, you could go do this, look at the sun, and hey, there's this little disk going right through this, and you can see what its color is. This particular one actually just literally screws into the top of this particular telescope here. It's a little miniature telescope whose job it is simply to do very simple chores like that. You can tell by the size of it and what it's all about. It's not really meant for anything great as far as science is concerned, but if you want to do a little quick observation of something, it's perfectly fine. It's a nice little scope, and you can look at the sun through it like that. Now, what else has been going on lately are these kinds of things, eclipse sunglasses. There is a little bit of caution to be had out there. NASA's been putting out some warnings about this, that as you might imagine, as we're getting closer to the day of the eclipse, these things are getting snapped up like crazy, right? I got these, by the way, at Walmart a couple weeks ago. As soon as they came out at Walmart, I quick grabbed a whole bunch for myself and my family and people that I'm going to be going seeing the eclipse with. They were only $1, so that at least at the time the cost was really reasonable. You do have to be a little bit careful about these kinds of sunglasses. one thing is, first off, regular sunglasses, absolutely no good for looking at an eclipse. That is something you should not do. Regular sunglasses are not constructed for that. These sunglasses in the hand, eclipse sunglasses, it's awesome look. They are otherwise pitch black. You are not going to be able to see a thing through these sunglasses. Again, that's their job, is to block that 99.99% of the light that you get, so it makes it visible. Now, I have tested these out myself. As soon as I bought them, I ripped them open and went out and looked at the sun, and they're in a parking lot of Walmart, so there's some crazy guy doing kind of stuff like this. And again, I saw a nice little round disc that's kind of a yellow-orangish color. Now, my advice would be for this, a couple things. First off, even with Eclipse sunglasses, I would not advise looking at this for the entire 3-hour stretch or so that the eclipse is going to last. That's not a good idea. I would say that look at it for a half a minute, maybe a minute or so, and then give your eyes a break. It is still decently bright, even with the sunglasses. Second thing is, as NASA and other people are starting to warn, because these things are being sold out, there's a lot of cheap knockoffs that are kind of cropping up, and the knockoffs will not necessarily protect you against ultraviolet very well. So one thing to do, NASA just put out a release to this effect. They have a list of manufacturers whom they trust, basically. Now, there is a certification that's drawn on the inside of the glasses. If you want to say, yeah, it has been certified such and such. I wouldn't necessarily trust that because, as you might expect, the people who are making the knockoffs just go ahead and print that on there anyway. And so it's not a guarantee that they're actually safe to look at. So I would say trust the sources of the people in the know. And so this particular brand is from the manufacturers on the approved list, in case people are wondering. But yeah, I would be cautious, a little bit cautious about that. Even with the Eclipse sunglasses, like I said, probably not the greatest idea to just stare at the sun. Give your eyes a break every once in a while. Another interesting trick to do, if you're wondering, well, how do I put these on and know where the sun is? Imagine, for example, the sun is directly behind you, folks like that. One thing you can do is turn yourself around like this, so that your shadow is directly, you're facing exactly away from the sun, and just simply do a full 180. And look up like that. You can see the sun that way. If you don't, this is especially good probably for younger kids who are maybe not as careful perhaps as they possibly should be. Questions?
It's related to that. How do you aim a telescope at the sun? I mean,
yeah, that's a good question. And I've been practicing with, we've got some department telescopes, and I've been practicing. I'm going to hook up a camera to it and hopefully get some pictures. We'll see how well I do when the eclipse day comes. But it involves that shadow trick. If you have a telescope, and telescopes have this sort of tube-looking appearance to them, right? Now, first off, for the telescope's sake, make sure the solar filter is already on. Because what will happen, it's not just the light that's bad, it's also the heat. The heat from the sun is hot enough that that's not going to melt the lenses or the mirror. It's not going to be that intense, but it could warp them. And glass, it turns out, isn't a perfect solid under these conditions. It flows very sluggishly, but it flows. And as most solids will do, it flows when it's warmer, a little bit better. So you want to have that protection on for the sake of the telescope, and of course any cameras that you might be using as well to take pictures with. But what I would suggest is, so you get it with the appropriate filter on it, and you get it kind of pointing towards the sun like that. So you're going to have the filter on first. But an interesting trick you can do is kind of turn around and look again at the shadow of the telescope on the ground. Now it's a tube, or cylinder shape, and almost all telescopes are cylinder shaped, right? But if you look at a telescope directly on, you don't see a cylinder, you see a circle, right? So if you can get the shadow as close to a perfect circle as possible, chances are you're pointing directly at the sun. And that is the trick that I use with a handheld type telescope. So that's what I have. I've got an old style telescope from the department, which means that I use controls. I have controls to manipulate, say, this way, and turn it this way, that sort of thing. And when I do that, I do my best to get it as close as possible, the shadow being a perfect circle on the ground. Then I can go ahead and do some fine tuning. And I found out with some practice, I've gotten pretty good at it. I can find the sun in a couple of minutes through the telescope. So it's something that can be done. Similar warnings for cameras. Now, the camera itself is, you're not the camera, so if you damage your camera, well, you've lost the camera. You haven't lost you or damaged your eyes. But similar sort of things to say. especially with digital cameras, you're not going to light the fire, the camera fire or anything like that. That's not going to happen. But you could swamp the detector on it. You could burn out some of the pixels, and then your camera won't work as well as it used to. So, why do that? Again, use a filter to cut down the light. It will be plenty bright enough. It's not an issue. The sun is still going to be easily seen with that. So that's some things about safety equipment. Now, there's another interesting trick. If you run out of everything, if you can't buy the Eclipse sunglasses, which is a thing, I went online to try to order some originally a month ago and found out I couldn't get them here in time. So it was already too late to order them a few weeks ago. And it's supposed that all the stores are sold out. And I heard places like Walmart and Best Buy and a few other places around locally where had them originally. They might be restocking, I don't know, but right now they're out. There's an interesting trick that you can use, and again, uses this sort of backwards idea. So, get a piece of hard cardboard, say, something like this, and get a push pin. Poke a hole, very tiny hole, right through the middle of it, like that, and you hold that hole up to the light this way. And so if you do that, so you get your hole in your cardboard like that, take a second piece of cardboard, or if it's good to just be on the ground, that's possible too. Just hold up so there's a place for that light to project. Light goes through the hole, and the hole acts like a camera. The original meaning of the idea of a camera is this idea to have a little tiny pinhole, and light goes streaming through the pinhole, and it forms an image on the other side. And so you can get an image of the sun like that by using this cardboard trick. So you don't need to actually have special filters or sunglasses. You can do this with just some stuff probably lying around the house. I would experiment a little bit with it first before you go out in the big day and you're filling around your cardboard and you can't get it to work. I would suggest, see if you can try, because this will work at any time. You don't have to wait for the eclipse to see an image of the sun through the pinhole. You can do this anytime the sun's out. So I would suggest doing that. NASA, again, was suggesting as an idea, if you want to make that hole really tiny to do a good job, not only just have the cardboard here, but then take something like, say, some aluminum foil and put the aluminum foil on here, paste it or tape it to the front of the cardboard, make that tiny hole through the foil, and that will give you perhaps an even better result that way. The one thing to kind of keep in mind when all's said and done, the sun is extremely bright, and even a small portion of the sun's direct light is not safe for people to look at. Okay. Give you an idea of what astronomers actually do real quick. These are some images of the sun taken through filters. The image on the left is through that neutral density filter idea I was talking about before, where all you're doing is cutting down the total amount of light that you see. On the right-hand side, we have something called an H-alpha filter. Now, H stands for hydrogen, and alpha just simply refers to a specific line in the ultraviolet. We'll show you a little bit of this in a moment, but hydrogen turns out as a gas can give off what are called spectral lines due to all the various electrons and all these various energy levels that they live in. And by looking at one specific line, so we're only looking at light from hydrogen atoms only in a very, very narrow window and ultraviolet on top of it, you can see the sun safely. One thing you ought to notice immediately is that it looks an awful lot different. That looking at the sun, this is just cutting down the light from the sun. You can see a couple of sunspots on there, but otherwise it's just what you might expect, kind of bland. Over here, when you're looking at the sun, you see an awful lot of activity. And so the general sense of it kind of looks like a cantaloupe almost, right? Kind of like that mottled surface or something like that. These are called granules in lingo, or granulation is the general effect. What you're looking at is basically the sun boiling over like a gigantic pot of boiling water. All these are bubbles coming up from down deep. They come up to the surface of the sun, so to speak, and they're popping. Each of these bubbles, the smallest of these bubbles is on the order of the size of our planet, to give you kind of an idea how big the bubbles are. But that gives you kind of an idea what's going on there. These pictures, by the way, are not identical pictures. They're taken of the sun at different times. These sections here, it looks a little bit brighter there and there. In the ultraviolet, that's where sunspots are in intense magnetic fields. And if you look very carefully, you might see a couple little bits kind of off to the edges here. There's a good one right there. That's called a prominence. It's a loop of material that's gas that's been thrown off the sun. The magnetic fields of the sun kind of take that gas, direct it into a big loop, and then haul it back down to the surface. And so the sun, it turns out, has a little bit of activity going on all the time. You can't tell that it's really active, but the sun turns out to be quite a dynamic object. One more thing to say about safety-wise, this is, we're not doing a huge amount of straight science here, but this is a graph of the amount of light that comes from the sun, what's called irradiance or intensity. And this is wavelength on the bottom, or color. And so in between these two green lines here and here, this is the visible light that's given off by the sun. So this is the stuff that you see. So Roy G. Biv, the rainbow, all comes within this general range right there. Over here to the left is a little bit of ultraviolet light. So roughly the sun emits about 3% of its power UV. And that's enough, by the way, that we always have to be a little bit careful about how we handle UV. And we put on the proper sunscreen or wear UV-coated sunglasses, that sort of thing. All the other energy on the right-hand side over here is due to infrared light. I will say also, by the way, these dips in here, that's due to the Earth's atmosphere absorbing some of the light of the sun. So the sun itself is maybe a little bit smoother if it was just the sunlight alone. But you can see there's a lot of stuff over here on the right-hand side. That's infrared, or what your skin can sense as heat. Here's another trick you can perform if you, say, go outside and it's still sunny out later on. You can close your eyes or shield your eyes like this, and I bet you can still get a sense as to where the sun is in the sky. One way to do that is to take your hand and kind of hold it up like this, right? And you can feel the heat of the sun on your palm. Your skin can sense infrared. You can't see it, but your skin can sense it. And so you'll feel the heat coming from the sun. And you get a general sense. You'll obviously get specific. You get a general sense about where the sun is that way. One of the dangers, probably the premier danger for looking at the sun, is not just the light from the sun, it's the heat from the sun. Your eyes have a lens in front, right? And it takes the light and focuses to the back. If you've ever seen a bright light and gotten spots in front of your eyes, that kind of effect, right? What's happened is that you've got a bright light and the heat has actually fused some of the chemicals in your eye into these big, large chunks. Now, fortunately, the eye is continually washing itself. It's always kind of moving along and continually like windshield wiping your eye. And so eventually those spots kind of move around a little bit if you notice, and then they fade away. That's because they've been washed out of the eye itself. But you can imagine if you keep doing this for a little bit too longer, or the heat is more intense, you can infuse not just some chemicals in the back of your eye, but you can start to actually burn a hole in the back of your eye. That's the real danger, is what it is. It's not just simply the light, the visible light itself, it's actually the heat coming from the sun that's actually probably, in a sense, a little more dangerous for people's vision. And it's stuff that you can't even normally see directly. Your eye doesn't sense this heat directly that way, but that's the damaging thing. So again, if you're going to be looking at the sun eclipse, and advise everybody to try it, keep all these various safety tips in mind. I want everybody to be safe and have a good time with this. So, what about the solar eclipse itself? Why is there a solar eclipse, or what is a solar eclipse to start with? And why do we have them more often than we do? Because once you understand how the system sort of works, you think, we should have a solar eclipse at least once a month. And this is the idea. So, I'm going to pretend that this softball here represents the Earth, and this little styrofoam thing represents the moon. And compared to each other, they're roughly about this size. The moon is about a quarter of the size across as the Earth is. That's not the same in other terms, but in terms of size across, or radius or diameter, that's pretty well like that. And the moon, of course, as people know full well, orbits the Earth. And imagine the sun over there that direction. If the moon's doing this around us, then once per month it ought to be coming in front of the Earth, right? So at least in theory, every month we should have a solar eclipse. And by the way, the other half of the month we should see a lunar eclipse where the Earth shadow covers up the moon. Same sort of logic, right? So why doesn't that happen? And it turns out there's a couple of details that matter. The first detail is that the sun and the moon are not perfectly, or the Earth really, are not perfectly aligned with each other. The Earth, of course, orbits the sun as well. So the Earth, you imagine going like this. The moon's orbit is almost, but not quite, lined up in the same way. It's actually tilted a little bit, sort of like this. Now I'm going to exaggerate for effect so you can see what I'm doing. But the amount of tilt is relatively small, only about 5 degrees. And so the moon is actually orbiting us like this. It's not this way. And so you have to have things lined up perfectly well. The moon has to kind of come down around its orbit just in the right spot while the Earth is moving in order for this eclipse effect to happen. So it's that small angle doesn't look like much, but it turns out to actually matter a great deal. So what does it mean? It means that, typically speaking, depending, the moon is either too far down, so to speak, or too far above, for the shadow to cross the Earth. And if the moon misses, the shadow of the moon misses us, then of course no solar eclipse. So that's the basic idea. Now, something that I often talk about in astronomy with my students a lot is scales, to try to get across to people how large the solar system really is, and how big objects are in comparison to each other. And so, Raj, if you don't mind, since you're right here, can you help me out with the demo real quick? I'm holding it like this, but the Earth and Moon are not really this far apart. Let's have you hold the Moon for me, please. And I'm going to roughly guesstimate here. If the Earth and Moon are to scale and we hold them apart the right distance, then they're roughly about this far apart. And when I do that, you can see it's a lot more difficult than for the Moon's shadow to hit the Earth. The Earth is a much smaller target. Okay? So that's what that, thank you very much. So that's what this means. The Earth is big in comparison to people, but in comparison to, say, objects in astronomy, not so much. And the Moon, of course, is much smaller still. If you want to talk about the numbers a little bit, I could say that the Moon is roughly 223,000 miles away, but that doesn't really help maybe, so what does that mean? Imagine the Earth here being about 8,000 miles across in diameter like that. You have to go about 30 Earths worth, if you will, out like that to get to the Moon. So that might be a better way to think about it. How many Earths do you have to travel to get to where the Moon is at? Maybe get you a better feel for how large the distance is between these two objects. The Sun, in comparison, by the way, the Sun is some 400 times further away from us than the Moon is on top of all that. So the Sun is really pretty far away. This particular picture here is showing it then to scale. There's the Moon on the far left, and here's the Earth on the far right. And that hopefully gives you a good idea as to why eclipses are difficult with this little tiny tilt. And 5 degrees doesn't sound like much, but if you have 5 degrees and you have 200,000+ miles to work with, it doesn't take much for that Moon's shadow to be above or below us. One thing else on kind of implicit with what I'm talking about here, the Moon's period of its orbit and the period of Earth's orbit are not in sync with each other. So the Moon takes about 27 1/3 or so days to orbit the Earth, and the Earth, of course, takes some 365 and some change days to orbit the Sun. And those numbers are not related to each other in any whole number factor at all. And so the Moon, I was demonstrating like this, but the Moon might be orbiting like this sometimes, but the next month the Moon might be tilted this way, the next month the Moon might be tilted over here, and so on and so forth. So the Moon's tilt, from where we see it, the Moon does kind of oscillate up or down as the year goes by. And so we don't see the shadow very often. So to give you kind of an idea how big the Moon, the full Moon is across, from our vantage point, it's roughly 1/2 degree. So it also turns out, by interesting cosmic coincidence, the Sun is also about 1/2 degree across right now. This hasn't always been true in Earth's history, by the way, if you go back far enough. But at the moment, it's pretty close to that. And if you're talking about how big the Earth looks like from the Moon, turn that around, the Earth is about 2 degrees across if you were on the Moon, looking backwards. So the astronauts way back, that's how big the Earth would look. So we don't have a full Moon right now. In fact, we're in the 3rd quarter phase of the Moon. So the next full Moon won't be for another 3 weeks or so. But the next time you have a full Moon, you can go out and look at that, and when you see a full Moon, and you see how big or small really that disk is, that represents about 1/2 of an angular degree. Give you kind of a feel for what that counts for in the sky. All this meaning to say, the Moon is tiny, the Moon's shadow is tiny, and the Earth is not that big a target in this context. So what is it? What are the consequences then? First off, a solar eclipse is not a common thing. Instead of happening once every month, as you might otherwise expect, you get a maximum of about 2 per year. It's more common to have 1 a year, but 2 per year is also fairly common. The solar eclipse itself doesn't last very long. The Earth, one more thing that happens, of course, is the Earth turns, right? And because of the Earth's rotation, where you are on Earth tends to kind of rotate through the eclipse or through the Moon's shadow and then back out again very quickly. And so from start to finish, from the instant that the Moon's shadow starts to cover the Sun to the moment that the Moon's shadow leaves the Sun for good, you get about somewhere between 2 to 3 hours is a pretty typical amount of time for coverage that way. And we'll see that in a little bit here. If you have a total solar eclipse, totality, when the Sun's completely covered up, that will last only a few minutes. So there's something, when people talk about how long an eclipse lasts, you do have to, or should, kind of distinguish between those two ideas. Here in Hattiesburg, I'm not going to have a total solar eclipse, but the eclipse from start to finish, when you get a tiny bit of a bite, say taken out of the sun with the moon shadow till the moment it ends, is going to run about 3 hours. So, and by the way, it'll be in the middle of the day. I'll show you the times in a little bit. So you can, it's not something, that, obviously, you know, as the joke was saying something before we started. When will this happen? Will it happen tonight sometime? Think about it for a moment. No, it's not. Yeah, of course. That's going to happen during the middle of the day. It only is the totality part doesn't last very long. Now, the moon's shadow is not very large, and so it doesn't cover up the sun completely. Or when it does, it's only for a few minutes that it can. And the last thing we can say about this is that because we're in different parts of the Earth, again, if I hold these up and again remind you that this is not to scale now, but the moon's shadow is not big enough to cover up the entire Earth at once, right? And so at any given moment, the moon will cover up even a tiny portion of the Earth to start with. Second thing is that the Earth does spin. So the Earth is spinning, and so while the moon's shadow might be covering up, say, a portion of the Earth, well, not everybody's going to see it because, you know, or it's not going to last, you know, the entire day because the Earth will spin and you'll rotate in and out of the eclipse, so to speak. And points north and south of the moon's shadow don't get to see it at all, or see a partial eclipse at best. So even if there's an eclipse happening, it's not necessarily happening for you, unfortunately. This particular eclipse is of very big interest to us because it is happening in the continent of the United States, which is, you know, nice for us. And even so, I'm going to have to drive some 500 miles to get to where I want to be to see the total version of the solar eclipse. So, one more thing now, or I want to go on and talk about the different kinds of eclipses you can have and throw in a few more ideas as to why they act. This is the moon's orbit around the Earth. I did stretch it out a little bit, not a lot, but a little bit to exaggerate. If you're wondering about terms, it says perigee over here and apogee over there on the left. Peri is a prefix in astronomy that means closest, and ap, it's not, you know, it's how you pronounce it. Ap is a prefix that means furthest. And so perigee, G is in Earth, or geo is in Earth, when the moon is closest to the Earth, apogee when the moon is furthest from the Earth. And one thing you should notice, and this is why I stretched out the picture a little bit, the moon is noticeably closer to the Earth here at perigee than it is at apogee, which means if the moon is too far away in its orbit, and the orbit is elliptical, it is stretched out, if it's too far away, it gets far enough away that the disk of the moon isn't big enough and it won't cover up the sun completely anyway. So it is possible to have the moon completely lined up perfectly well, but you don't get to see a total solar eclipse because the moon is too far. So it's not a guarantee, even with all those other things going on, that you can get a total solar eclipse. Now, for us, and the statistics for this particular eclipse, what's going on, this particular eclipse, the moon will be close enough to cover up the sun. Depending upon where you live, the longest duration of totality, when the moon completely covers up the sun, will be about 2.5 minutes long. I'm going to be in Greenville, South Carolina officially, and it's about 2 minutes and 10 seconds there we'll have. If you're not in that line of totality, then you're not going to see, of course, the total eclipse. The longest possible eclipse you can have, which means that the moon is at perfect perigee and is perfectly lined up to give you an eclipse, you get a maximum of 7 minutes. That's the longest totality can ever last. You can't go any longer than that. That's just, you know, the moon is as close as it's going to get, is as big as the shadow the moon's ever going to get to do that. So, what are some of these kinds of eclipses then? Well, here's what we're going to see some of us are going to see, if you tend to travel for that. This is a total solar eclipse. I'll talk about what you're looking at in a few minutes. This is called an annular eclipse. Annulus, or annular, just refers to the idea of a ring. And so as you can kind of tell, now that I've said it, there's a ring of sunlight surrounding the moon. So even though the moon is perfectly lined up, you don't get to see a total solar eclipse. One of these happened in the 90s. That was the one I was talking about before with Dark Element there. This is more closer to what you're going to see in Hattiesburg, is a partial eclipse. In fact, everybody's going to see this general effect. If you're in a line of totality, you'd get just a couple of minutes of totality. Most of the day, you're going to see something like this as well. So when we talk about a total solar eclipse, we really mean that it's only going to be total for those few minutes where the moon's perfectly lined up. The rest of the time you have an eclipse happening, it will be partial. So partial eclipses are the rule. That's the thing that always happens, guaranteed. Whether you have an annular eclipse or a total eclipse depends then on, are you lined up perfectly with the moon's shadow, and is the moon close enough to cover up the sun completely or not. So these, in other words, are special cases here and here. This is something of the light that everybody gets to see, that, so partial eclipse there. Why is that the case? Well, it turns out that the sun is bigger than the moon, as I'm sure people are aware. Roughly 400 times larger across than the moon is. And if that number sounds familiar, it is the same number I cited earlier. It turns out that works out that way. And because of that, the sun although the sun is extremely far away, it does cast the light from the sun does come in at a little bit of a shallow angle. And again, I've exaggerated the angle for effect so you can see what's happening. The darkest part of the shadow, in other words, if you're directly behind the moon and you can't see any sun no matter what, it's called an umbral part of the shadow. If you're in part of the shadow, on one side the sun's covered up, so if you're over here, some of the sun's covered up, but some of the light from the sun's getting to you, it makes what's called a penumbral eclipse, or penumbral shadow, excuse me. And this is one that's kind of interesting. If you get far enough away, you see what's called an antumbral eclipse, strangely enough. And those correspond to the types of eclipses I just got done talking about. So, if you're in the umbra of the moon shadow, you get a total solar eclipse. If you're in the penumbra, you get a partial. And if you're in the antumbra, you get what's called an annular or ring eclipse. So that's why the names of the shadows aren't super important, and those are kind of those extra nerdy type of details that astronomers like to throw out, right? So that's not something that you really need to worry about when you're actually observing an eclipse. But if you want to know why you're seeing what you're seeing, it tells you that. Let's go back to the map here a little bit. Does this mean that nobody else gets to see an eclipse in the United States? The answer is no. You have to be along this arc here that's been shaded in if you want to see any part of totality. So roughly say starting over there in the Pacific Northwest, see Salem in Oregon is that little red dot there that's inside the shadow. Kansas City is right here at the edge, so parts of Kansas City will get a total, and some parts will not. St. Louis is on the other edge of it, strangely enough, and so again, parts of St. Louis will have it and parts will not. In fact, they've already did this. I didn't include this with the presentation, but there's a street map of St. Louis that's already been made. If you're on this street, you get a partial eclipse. If you cross the street, you're in the total solar eclipse. Kind of wild. Yeah, so Clarksville, Tennessee is almost dead center, so that's like the best place in the world currently to watch this one. Let's see here, here's Greenville, South Carolina. There's several Greenvilles, by the way. I have to make sure I tell you which Greenville I'm going to. If I go to Greenville, North Carolina, I'm going to kind of be out, miss the boat here, right? Or Greenville, Mississippi, or Greenville. Every state has a Greenville, right? I think it's just one of those things. But here's Greenville, South Carolina. So I'm not perfectly dead on, but pretty close to it. Columbia, South Carolina, and there's Charleston. Give you an idea there. Oh, what about Hattiesburg? Hattiesburg's over here, right? It's not labeled on this map, but that's where Hattiesburg is. So we're definitely a decent piece away from where the totality is going to happen. But we still are going to get a partial eclipse. You're not going to get the sun completely covered up, but you will get about 80% or so covered up. So go ahead and skip around a little bit. Here's some other interesting stats for the eclipse. And I've got a close-up here to kind of get a feel for this. This, by the way, is cutting through the middle. If you lived in South Carolina, you're in like, this is perfect. The width of the eclipse itself is roughly about 70 miles. So from here to here, that's about 70 miles wide. And the speed of the shadow is a little under 1,500 miles per hour. So now, what's that due to? Most of that is due to the fact that the Earth is rotating, but there's also the fact that the moon itself is moving. The moon isn't standing still. The moon actually orbits the Earth, right? And of course, the Earth also orbits the sun at the same time. So all these motions combined together give you a pretty large number for speed. I've heard people describe it this way who've seen a total solar eclipse, is that they can actually, if you're at a reasonable height and you're in a flat area, you can actually see the dark shadow on its way. And it just like comes in a rush. You can kind of watch it coming in. I'm going to be in a metro area, unfortunately, so I won't probably have that effect, but I've heard people talk about that way. So. How about time strategy? When are you going to, if you're going to stay here, let's assume that you're going to be here, when are you going to see the eclipse? The official term for it is called first contact, which sounds like a movie title. This particular first contact just simply means when the shadow of the moon first starts hitting the sun, right? And that'll happen at 11:57 and 39.0 seconds in the morning. These, by the way, are local times, so this is not like you don't have to like translate back from daylight to regular time or anything like that. This is local, it's Central Daylight Time, we're in its own. One thing to point out is that it's accurate to the 10th of a second, by the way. Again, to give you, to pump up my profession a little bit here, we do have a good ability to tell these things ahead of time. Maximum coverage is going to be roughly around 130. So again, that doesn't mean you're going to get a total solar eclipse, but about 80%, give or take a little bit, is going to have the sun will be covered up. So most of the sun, in other words, something that might look approximately like this, maybe this picture, probably this one right here, you'll get a sliver of sun, kind of a crescent sun, in other words, will kind of be poking at you. But it will never get more than that. You'll always see it. You'll have a crescent sun, and then the crescent will start getting bigger again once 1:30 passes by. And then the eclipse ends, or the last contact, or final contact, is a little bit before 3 o'clock in the afternoon. If you look carefully at the times, you'll see that the from start to finish is about 3 hours. So, in other words, if you're interested in just seeing an eclipse, part of an eclipse happening, and I don't suggest you have to stand out there and watch the entire 3-hour event. I think I wouldn't do that. But it gives you an idea of when it's going to happen. It's in the middle of the day, right? And so you can go off and do whatever. You're in class, you're at work, whatever. You come outside, you grab your eclipse sunglasses, of course, and you look at it, maybe snap a cool picture, and then go back inside for a little while, and then come back out, say 15 minutes later, to see if it's changed or not. This path is, and I did make this clear, but because the Earth rotates in the way it does, primarily, the eclipse is going to start in the Pacific Northwest and go across the country this way towards the southeast. So that's the direction it's going in. And so just for fun, because I know it means nothing to the rest of you, but it means something to me, this is what I'm going to be seeing now. And again, these are local times. They're in the Eastern time zone there. So if you want to change times to an idea when they're going to see it, you can tell what that's going to be. In other words, actually, if you look carefully, if you change it to Central Time, maximum coverage is about 139, and it was, what, 127 for you here? So it's only another 12 minutes later, and I'm going to see the same thing you're seeing, say several hundred miles off to the east. So again, it gives you kind of an idea how fast the actual shadow is traveling. But those are the official times, say there, if you're interested. Different times, of course, for different locations. I've done this. Just real quick search for eclipse calculators or things like that, and they'll immediately tell you for your location when the eclipse is starting, when it's going to hit maximum, when it ends, how long it's going to be, what maximum coverage is going to be percentage-wise, all those things for pretty much any location in the United States. You can find that out within a couple of minutes. So, in other words, I didn't calculate that from first principles, is what I'm saying. All right, now, what are you going to see? So let's suppose you're lucky and get to see totality, or later on you see pictures of it. What exactly are you looking at? What are you going to be seeing? Well, first off, the black there, of course, that's the moon shadow there. That's going to be about as dark ever gets, because we're not used to this. Even when the moon, you can even see the moon during the daytime sometimes, right? So we're used to seeing the moon when it's available, but in this case, we have the moon blocking out the shadow blocking out the sun, and we're in the shadow of the moon itself. So we're taking away the sun's light, and we're putting darkness on top of it. It's going to be it's going to look like a pitch hole, black hole has been punched right in the sky for a few minutes, is what it'll look like. So that's one thing that'll happen. But what's all the rest of the stuff around it? And it turns out that the sun isn't just a disk, or just a big ball of stuff. What is the sun? The sun is an object with lots of layers. It's got a lot of structure to it. And the problem is that most of the time you can't see that, because the part of the sun we do see is so much brighter. The portion of the sun that we look at, or experience, I should say, because I don't want you going out there and looking at it. Dr. Sirola said, go look at the sun to see what, no, I didn't say that. But the portion of the sun that you see with the naked eye is called the photosphere, literally the light sphere. And that's the portion of the sun that the visible light finally gets here from the sun. If you go deeper to the sun's too thick and doesn't tend to let light through. If you go further above the sun, away from the sun's surface, then the gas gets much thinner, and it's not generating this kind of light. So there's a layer about 200 miles thick or so around the sun, which we call the photosphere. Now the sun itself is roughly 1 million miles across, And so while 200 miles sounds relatively thick in normal people speak, and I'll agree there, 200 miles compared to 1,000,000 miles, it's thinner than the skin of an apple, is what the photosphere is for us. So it's not correct in a sense to say that the sun has a surface. You definitely couldn't stand on it, it's not solid anyway, and all that. But from a distance, the sun does have a definite sharp appearance to it, and that's the photosphere. The photosphere is about 1,000,000 times brighter than every other part of the sun. And that's why during normal days, you don't see anything else but the photosphere. The photosphere easily wipes out or washes out anything else that you'll see from the sun. But there are other layers, and what do you see? Well, you see a little bit of it here. If you look at this picture, it's taken in color on purpose. There's a lot of pink kind of around the edges. Where's the pink coming from? This is a layer called the chromosphere, the color sphere. And what's happening is that as you get further and further from the sun, the density, the thickness of the gas is getting less and less, and that allows gas to give off what are called spectral lines. Now, we're not going to do a whole big lesson in atomic physics here, but I can tell you that every atom or molecule too has what's called a specific spectral signature that given the various different energy levels that electrons live in, they can bounce back and forth between these levels, and if given the chance, they give off energy when they make a jump, and it's possible to see light when they do that. So just to kind of show off what this is I borrowed this from one of our classrooms. This is just a little power supply that I've got hooked up to a little tube of gas here. Let me take this out to show you what I've got here. This little tube here has hydrogen gas inside it, very thin hydrogen gas. There are little metal contacts at the ends, and inside these barriers here, these guards, are some metal springs to make the electrical connection. And when I turn on the power, what I'm doing is sending electricity through this thin gas. What that does is gives energy to the electrons, bounces them up to higher energy levels, but electrons, it turns out, don't want to live there, so to speak. And so they tend to drop back down to lower energy levels where they're more likely to be. In the process, they give off light, and it looks like this. And if you compare this color to that color, you'll see kind of the same thing, aren't you? Very similar in color. That's because that's what you're looking at. 90% of the sun by number is made out of hydrogen. 9 out of every 10 particles in the sun is hydrogen. By the way, just to throw out the other numbers, 9 out of the other 10 remaining particles is helium, and then the rest of the sun, all the other elements that we can imagine, that makes up 1% of the total. The sun and most astronomy objects are hydrogen and helium rich. The Earth is kind of an exception to that rule, actually. But that's what you're looking at. You're looking at hydrogen gas that's being excited. Now, there's not electricity. It's not like somebody's got a big battery or something up there, right? Something's happening. But you don't have to do it with electricity. You just need an energy source. You need some energy. And that's energy by and large coming from inside the sun further. It's trying to escape. Bumps these electrons up to higher levels. They drop back down, and they give up this energy as light in the process, and that's what you see. So that's called the chromosphere. The chromosphere is thinner than the photosphere, but it's hotter as well. It's vacuum thin by Earth standards, it turns out. So it's reasonably thinner. That's not the real spectacular stuff. The real spectacular stuff is the stuff all over the place on the outsides, right? That's called the solar corona. The corona is a word for crown, by the way. You get that by, say, a coronation is when you put a crown on a new king or queen, right? So corona is that idea. And the solar corona is a region that's a little bit further up from the sun. It's higher in terms of temperature and even less in terms of density. Now, the corona does not have a specific shape. It changes literally from day to day. So if you see some other pictures from either me showing you here today, or you see some other pictures later on of the eclipse that's going to happen next week, you'll probably see a different shape for the corona. And that's okay. The corona is not very well bound to the rest of the sun. The corona is so far from the sun and is so energetic that a lot of the stuff is starting to stream off, and some of it even escape the sun's surface, escape the sun's gravity completely. And so, and depending upon what the sun is doing, how active the sun is, there's a storm over here, there's a flare over there in the sun, you might have more corona over in this direction than that direction from day to day. And so the corona doesn't have a specific shape to it. It does extend out hundreds of thousands, not millions of miles out into space. Here's a separate picture to give you again the idea of the corona. The average temperature of the corona if it makes sense to talk about average temperature for something like this, is about 2 million kelvins. Several million degrees Fahrenheit, if you prefer that. By the way, at some point, scientists just give up. We don't talk about Fahrenheit at this stage. We're like, that's ridiculous. We might as well just use what normal scientists use. In any case, it's kind of a weird thing. Why is it that the sun's corona is so hot? Because, after all, it's further from the sun. Now, there's nuclear fusion going on inside the heart of the sun, which is giving it its energy in the first place and keeps it extremely hot, and that makes sense. And it makes sense as you go further and further outward from the sun, the temperature should be dropping. But actually, for a while, you get past the photosphere, and the temperature starts to rise again. And why is that? When the solar corona is extremely hot in comparison, the photosphere is only in quotes, about 6,000 kelvins. So this is a really big jump in temperature, and why is that the case? This is one of the bigger mysteries still to talk about in solar astronomy, that astronomers have still not yet come up with complete explanations for why this is as hot as it is. We have most of it covered, if you will, so to speak, but the details are still being wrangled around with. So how would you heat up a gas? Well, you can have a storm in the sun, an eruption of like a flare, some event like that where you blow a huge ball of gas comes literally exploding off the surface of the sun and goes to the corona, and that shock wave that heats up the gas. The sun has a very large magnetic field, and a lot of energy gets moved back and forth around by the magnetic field of the sun. And so there's a little bit of energy stolen from the sun's magnetic field to heat up the corona gas. But most objects, even if they're heated, eventually cool off, right? Now, if you take, for example, a lump of charcoal and say you're cooking out, I don't know why you cook out today. I mean, you just put the slab of meat out there on a day like today, right? And then just wait a little while and it's already cooked for you. You don't need to actually fire up the grill. Let's suppose it's reasonably cool so you can go out and fire up the grill and actually cook up. When you're done, the coals will slowly, if they got up to that nice orange color, then they'll slowly fade away, right? And eventually they become cool again. And it takes maybe a couple hours, and you could go and pick up that piece of used up charcoal and it's perfectly safe, right? Part of the story behind that is that a lot of the particles, a lot of the atoms inside that charcoal are near each other and they collide. And in the collision process, smacking back and forth against each other, they tend to give up energy and emit light and heat. And that's what they're doing. You can't do that with the solar corona. The solar corona is so vacuum thin, it's very rare for one particle in the corona to actually meet another particle in the corona. And so these individual particles gather all this extra energy from things like solar flares and magnetic storms, but they can't get rid of it. They can't cool down, in other words. This is a really kind of a weird process. That's the majority of the story for the corona, and why it just looks like it does. Now, the corona and the chromosphere are not subtle things. Turns out that they are about as bright as the full moon is. And a full moon in the night sky is pretty bright, right? It's pretty easy to see the full moon. But again, it's all in comparison to the rest of the sun. The photosphere is a million times brighter still. So when we have a total solar eclipse, we cover up the photosphere, the corona pops out. It doesn't, you don't see nothing. It's not where the sky becomes completely pitch black. It doesn't happen. You get kind of a twilight sort of effect. And you get, it's dark, but it's not pitch black because the corona and the chromosphere do still light up the sky a little bit.
Are you going to be able to see totality through eclipse glasses?
No. Yeah, that's the thing. You won't see totality through the eclipse sunglasses. So when totality actually hits for good, you take your eclipse sunglasses off and you can see it. That's the few minutes where you can look at the sun and and even then, just be cautious.
Yeah, because it ends.
Because it ends pretty quickly. Right? Yeah, so totality, that's another reason to have the clock as precise as we do, is we don't want to, we want to be careful with this. Now, I've only got a few minutes left here. I'm actually going a little bit over time, so let me speed up to a couple more things that you're going to see. Here's another effect that's seen during the total solar eclipse, and this is really a wild one. It's called Bailey's beads. Bailey was an English astronomer in the 1800s. He's not the first person to see this, but he's apparently the first person to have his name attached to this effect. The moon isn't a perfect sphere. The moon has mountains, craters, valleys, and that means that the moon is a little bit jagged around the edges. And so when the moon covers up the sun, or tries to cover up the sun completely, sometimes sunlight can get through some of those valleys. And that's what you're actually seeing here. It looks like beads. It looks like little dots of light, kind of like a necklace of some kind, right? But these beads aren't beads at all. That's sunlight making it through the valleys of the moon. That's what that is. You get a different effect for different eclipses will have different Baily's beads because the moon will be oriented slightly differently each eclipse. If you take that to the extreme, right at the very beginning of a totality or right at the very end of totality, you get something called the diamond ring. And once I say it, it's kind of obvious what we're kind of looking at, right? It's the same effect. It's Baily's beads taken to a little bit further level. And it's only visible for a couple seconds. The diamond ring effect lasts for a few seconds and then it's done. Either you're into totality or you're out of totality. So it's a very quick thing to sort of notice. But if you get the diamond ring effect, again, light from the sun is passing through one particular valley right here, and it's just creeping up enough that you're getting a little bit more of the sun around the edges of the moon, and you get that really neat effect.
See stars and things like
Yes,
that with your naked
I'm
eye?
going to show you some pictures of that in a moment. Yeah. So, now, what have people done for scientists? Now, you might be familiar with this guy. There's an old thing called Halley's Comet, right? Halley was a historian of astronomy. That was his love, is to dig through records of old astronomers and try to figure out what's going on. And that's why he got the comet attached to his name, because he predicted when a comet would return. But it wasn't the only thing he predicted would return. He currently also predicted from old records when the next eclipse would happen. And pretty good precision in those days. We're talking 300 plus years ago. And you're within a few minutes, not bad for those days. Here's something else I wanted to show off. Can you actually get any science out of this besides just looking neat? And well, it turns out you can. I mentioned before there's an element called helium. And let me bring that up real quick since I've got this here. So this is what helium looks like if you just look at it in general. And helium is a different element than hydrogen. And because it's a different element, because it has different numbers of electrons in different places, it has different energy level differences and gives off different spectral lines. The electrons jump differently, if you will, in helium. Well, nobody knew of helium on Earth until this happened. Jules Janssen, I want to say he was originally from the Netherlands, but I think he was working in England at the time. Don't quote me on that one. But he was using a spectroscope, which was a pretty brand new thing to do in those days, by the way, and saw some lines that didn't agree with anything else that he knew about. And after a while, realized that this is a new set of lines that are coming out of the sun. And he nicknamed it helium, as in Helios, the Greek god of the sun. That's why it has its name. Helium was discovered in the sun, and specifically during a total solar eclipse, before it was discovered here. So people have used it for a little bit of science, turns out, not just pretty pictures. Here's the other great science thing I want to talk about. It goes back to the question about the stars. You can see stars, but it's a little difficult, at least to get pictures of it. You'll see stars far away from the sun. This was pretty close to the sun. This was an event that's very famous in the history of science. The particular astronomer involved was a guy named Arthur Eddington. He was from England, but he had to travel for the eclipse. He was actually off the northwest coast of Africa on an island to do this particular observation. Now, it's not visible from here. In fact, it's not really visible from me. I know what I'm kind of looking at. But there's a couple of small dashes here and here that he used to mark off the positions of a few stars. These particular stars belong to a cluster of stars called the Hyades in the constellation of Taurus the Bull. Why does anybody care what he's doing with that? Well, here's a guy named Einstein who had predicted an interesting thing could happen. Einstein's version of gravity, or general relativity, suggests that gravity is not really a force in nature, but rather that gravity is a warping of space and time, and that objects tend to follow the curvature of space as they move around. And he had predicted, he heard about this eclipse, and he predicted that if you look at a particular star in the sky, the star will appear to have moved position. Now, the star won't have gone anywhere, but because the sun is a very large object and has a very large amount of gravity, it warps space around it very intensely. The path of light from that star will be shifted a little bit. Now, not a lot, but a little bit. I don't think you can read it from there, but it only says 1.75 arc seconds. I will tell you this, an arc second is not something you can see with the naked eye. It's too small. You do need equipment for that. We need a telescope in order to pick up an angle that tiny. But the star is actually here, but because the sun's gravity bends the light, it makes it look like it's coming from over here. So there's a apparent shift in the position of the star while the sun's in front of it. Now, that's happening all the time, by the way. This is not something that's only during eclipse. The sun's doing this all the time. It's just that you can't see it, right? Because the sun's big and bright and washes out everything again. But during a total solar eclipse, Eddington, go back up this page for a moment. This is what he did then. He had a research grade telescope back then. You still do that. This is old chemical photography, but that was perfectly fine. And so this is a negative picture of it. So the sun, this is the shadow of the moon on the sun there. Here's the corona. And off to the side are some of the stars of the Hyades, some of those particular stars nearby. And he was able to show that they were shifted, that their positions were not the same as they would otherwise be if you just looked at the stars by themselves. And because that corresponded to what Einstein had predicted, that was evidence for Einstein's theory, that Einstein's general relativity idea is correct. So, all right, last things we're going to talk about, when's the next solar eclipse? This is a map showing the map of the world, and the shadings down over here tell you that, well, if you live in the South Pole, you can see an eclipse. If you don't live in the South Pole, not so much. So yes, it will be true that in February, upcoming, there'll be a solar eclipse, but like I was saying before, it doesn't happen for us all the time. It's going to be happening for somebody else. And so somebody else is going to, so the next solar eclipse. This is the next solar eclipse that's going to happen in the Americas. This will be an annular eclipse. So that ring effect we were talking about before. What we see here is that these dark lines are the regions of totality. So if you look, it's going to go from the Pacific Northwest, but it's going to kind of come up short a little bit of time. It's going to go through the middle of Texas here. And then actually continue through Central and South America, actually. The reason it comes to an end is because at this point the Earth has rotated and the moon has moved far enough that the moon's shadows miss the Earth down. So it comes to a sharp point there where all of a sudden the moon's shadow is no longer there to make an eclipse. That's why that does that. These other bands here are percentages by 10% off. So 100% coverage in this thick band in the middle, 90% of the moon will be covered, roughly speaking, in these bands here, 80%, 70%, and so on, going upwards like that. You can see Hattiesburg is roughly about there, so we're going to be, again, around 80% coverage. But if we come back around, and this will be, what, 6+ years from now, we'll have another solar eclipse in the country, and again, we'll have a similar sort of thing happen. The difference here is that this is an annular eclipse. It won't be a total solar eclipse, so nobody gets to see total. Even in this band here, you don't get to see total, you just get to see the moon perfectly lined up. You see that big circle with a ring around it. But you don't get to see a total solar eclipse. How about the next total solar eclipse? The next year after that, turns out. April of 2024, so 6.5 or so years from now. The next total solar eclipse, and again, same kind of idea, same map. Again, unfortunately, we're going to miss it. We're going to miss the totality part. So again, Hattiesburg is roughly around here, right? So again, we're in the 80% range. And somebody over here is going to get it. Now there's some lucky place in the country where this year's eclipse is coming down like this, right? And that eclipse is going like that. There's some lucky place right around in here that's going to get 2 total solar eclipses, which we are not. So, lucky dogs.
Does that go through Dallas? Looks close.
It might be close to Dallas. I'm not as familiar with Texas as maybe I should be. Yeah, Texas is going to have some eclipses. New England gets it pretty well. Or Maine is going to have a nice eclipse here, for example. So, but yeah, those are. By the way, I didn't take it any further than this for the talk purposes, but astronomers can pretty much predict eclipses out to the second, a good century or so into the future. And if you really want to push us, you could probably have solar eclipses out for a few thousand years to have at least what day and rough time it's going to happen. So you kind of have a decent handle on this, if you will. Yeah, so it's not actually that long. So the last total solar eclipse in the United continent of the United States was in 1979. So that was almost 40 years ago. But we're going to get 2 total solar eclipses in the country within a span of less than a decade. So hang on, if you don't get to travel this time, make your plans. See if you know anybody that lives along the stretch, and check out the eclipse. Thank you very much, everybody.